We use chemical equations to represent chemical reactions, to state them in a way that's very clear and concise, and it actually transcends different languages, so that's nice as well. On the left side of the arrow, so here's an example of a chemical reaction. This is the reaction of methane, which is the predominant gas in natural gas, reacting with oxygen to form carbon dioxide and water. So it's like a math equation. Here we've got something plus something, but instead of an equal sign, we have an arrow. The arrow indicates a direction. We're going from this to that. So on the left of the arrow, because we read left to right, these are the reactants. That's what reacts. And over here we have the products on the right side. It points to the products. The reactants react to produce the products. We're not trying to be cryptic here. We often, but not always, indicate the physical state of each reactant or product in parentheses. So methane is a gas here, and oxygen is a gas, and we're forming carbon dioxide as a gas and water as a gas. If the problem that you're doing says to include state symbols, then you sure as heck better include the state symbols. If it doesn't specifically say, then you could go either way. So here are the state symbols. G means it's a gas, L means it's a liquid, S means it's a solid. Just the first letter of each of those three states. And then we have AQ. AQ stands for aqueous, which is similar to the Spanish word for water, agua. This just means it's dissolved in water, an aqueous solution or a solution in water. And the reason we have a special term for that is because so many different reactions occur in water that is just very useful. So, in this example here, CH4 plus O2 forming CO2 and H2O. If we look at models of this, which can be very helpful, sometimes we need some pictures. And I have model kits upstairs. If you ever want to use a model kit and play around with it, if you're a very tactile person, I'd be happy to let you play around with one for a while. Because once you make that connection between what those balls are doing and what the symbols are, it makes the chemical equations much easier to understand. So here's methane. 1 carbon, 4 hydrogens. So we have 1 black one and 4, they really should be white, but white's hard to see, so they're gray. And here we have O2, that's 2 oxygen atoms. These are going to react. We could think of these as Tinker Toys or Legos, and we pull them apart and we make these two things. Could I take this and make these without using extra pieces and without having anything left over? No, I couldn't. Because over here, I've got 2 red balls, and over here I've got 3 red balls. Where does the third red ball come from? Conservation of matter says that atoms are not created or destroyed in a chemical reaction. So that's impossible. And then what about these hydrogens? There's 4 white balls here, and there's only 2 over here. Where did they go? Well, nothing happened to them. Our equation is wrong. This equation is not a good description of what's happening. So here's the other problem, the 4 hydrogen atoms here and the 2 hydrogen atoms over there. So we need to adjust our chemical equation. We need to balance it so that we have the same number of hydrogen, oxygen, and carbon atoms on the left side as we do on the right side. That's called a balanced chemical equation. So, looking at the pictures, if we had 1 of these and 2 of those, then we could make 1 of these and 2 of those and not need to pull in any extra pieces and not have any left over. You see that? Now we're starting with 4 white balls, and because we've got 2 of these guys, we can have 2 whites and 2 whites, that's 4. And here, by throwing in another oxygen molecule, now we've got 4 red balls to start with, and over here we end up with 4 red balls. We started with one black one, we end up with one black one. To indicate this in our equation, we just put a number in front of the formula. 2, O2, means 2 oxygen molecules. It's not an oxygen molecule that has 4 atoms bonded together. Oxygen molecules are diatomic 2 atoms. This is just saying I have 2 of them. And over here, 2 water molecules. There's one water molecule, and there's the second water molecule. Why don't we write a 1 in front of the CH4? Because chemists seem to have a thing about writing the 1. We don't write 1s unless we have to. So we're not going to put a 1 here, and we're not going to put a 1 there, but we understand that there's got to be 1, or we wouldn't have written the formula at all, and if there was going to be more than 1, we'd write a number. Any questions? It's really important to understand how this equation represents this happening.